I did is I wrote the equation that we have to balance. And even though it has all these terms in it, this is all this stuff here, all the way over to here, is 1 mole of fuel. So we're balancing the equation for 1 mole of fuel. So these percents are all based per mole of fuel is 67.4% carbon, blah, blah, blah. So it's 1 mole of fuel. And now we go through the same process for complete combustion of balancing what's on the left and what's on the right. So, and we have the unknowns here, so I don't know what C, D, E, and F are, and we'll find those out. And we're doing this for 100% theoretical error. So we have the carbon balance. And so I see that C is equal to 0.674. It's the only carbon in the equation. I have an H balance. And over here I have 2D. So if I look, I have hydrogen here and I have some hydrogen in here. So I have to account for all the hydrogen. So if I start off with 2D, 2D is equal to 2 times 0.274 here plus 0.023, or we get that D is equal to 0.297. And I do the sulfur balance. And again, in this case, E, there's only sulfur here, so it's 0.003. And now we have a tricky situation, a slightly tricky situation, because I want to do the oxygen balance. So I do the O2 balance. Let's see. I have an O2 here, I have an oxygen here, and I have an oxygen here. And so I need to pay attention to those on the input side. On the output side, I have the oxygen here, here, and here. So on the input side, I have, so on the reactants, I have 0.021 plus 0.023 divided by 2 plus A. So this is the oxygen going in to the reaction. And on the product side, I have C, which is 0.674 plus, I have for the water 0.297 over 2. I have for the sulfur 0.003. So then A is equal to 0.792. And now I have the same sort of deal with the nitrogen, because I have the nitrogen here as well as the nitrogen here. But now I know what A is. So we're going to do a nitrogen balance as well. Erase all this. Oops, I didn't mean to erase that. Where am I? And so for the N2, we're going to have 0.005 plus 3.76 times 0.792, and that's going to equal F. So F then is equal to 2.983. Now I can find the air-fuel ratio on the mole basis. So RAF would be equal to 0.792 times the molecular weight, 28.97, divided by 1. So this is equal to 3.77 moles of air per mole of fuel. Oh, I did this wrong. That's the mass basis, so I need the number of moles, which is 4.76. It's a challenge sometimes reading my own notes, so I do run into that problem from time to time. I have to check that. And now but this is fine, but what's interesting, more interesting, is on the mass basis, so we need to find the molecular weight of the fuel. We know the molecular weight of the air, 28.97. We need the molecular weight of the fuel. And so that's the sum of the YI, molecular weight of the coal, is equal to the sum of the YI MI. So I will write all this out. So that's what we have to find next. And so we take the YI of the fuel and we multiply it by each of the constituents' molecular weight. So the molecular weight of the coal is equal to 0.674, the carbon, times 12, plus 0.274 times 2.016 plus 0.021 times 32 plus 0.003 times 32 plus 0.005 times 28.016 plus, lastly, 0.023 times 18.016. That's a lot. So anyway, if I multiply all that out, I get the molecular weight of the coal is equal to 9.96 kilograms per kilogram mole. And the RAF is equal to 3.77 the moles of air times 28.97 the molecular weight of the air, divided by 1 mole of fuel times its molecular weight, 9.96, and that's equal to 10.96 kilograms of air per kilogram of fuel. So this tells us that I'm burning coal, then I need about 11 kilograms for each kilogram of fuel that's used. And if I look at a metric ton is 1,000 kilograms. That tells me what my air supply has to be to burn a metric ton of fuel, of coal. And so that's why we like these things on a mass basis. It enables us to do that.